State and prove the Hamilton principle. Now statement: the motion of a system from time t1 to t2 is such that the line integral I is equal to integral t1 to t2 L dt, where L is t minus v, is an extremum for the path of the motion. No solution. Let us consider a system in which is consist of n particle of mass m1, m2, so on mn. Now let us assume that their configuration with respect to an inertial frame is given by r1, r2, so on rn. By D'Alembert's principle, we have sigma I varying from 1 to capital N. So bracket starts Fi minus Pi dot bracket close delta Ri is 0. Or sigma I varying from 1 to N, small bracket starts Fi minus Mi Ri double dot small bracket close delta Ri is 0, which is equation 1. Now here Fi is the applied force acting on the particle. The kinetic energy of the system T is equal to half sigma I varying from 1 to n mi Ri dot square. So variation of kinetic energy is given by is equal to delta T, which is equal to delta small bracket starts 1 upon a half sigma is varying from 1 to n mi Ri dot square bracket close, which is equal to sigma I varying from 1 to n mi Ri dot into delta Ri, which is further equal to d over dt of bracket start sigma I varying from 1 to n mi Ri dot delta Ri bracket close minus sigma I varying from 1 to n mi Ri double dot delta Ri, which is equal to d over dt bracket start sigma I varying from 1 to n mi Ri dot delta Ri bracket close minus sigma I varying from 1 to n Fi delta Ri, which is equal to delta T plus sigma I varying from 1 to n Fi delta Ri, which is equal to d over dt of sigma I varying from 1 to n mi Ri delta Ri. Now integrating with respect to t between the limits t1 and t2, we get integral t1 to t2 bracket starts delta t plus sigma I varying from 1 to n Fi delta Ri bracket close dt is equal to sigma I varying from 1 to n square bracket starts mi Ri dot delta Ri square bracket close t1 to t2. Now configuration of the system as specified at a time t1 and t2 such that the variation of delta Ri vanishes at these times. So integral t1 to t2 bracket start delta t plus sigma I varying from 1 to n Fi dot Fi into delta Ri bracket close dt is equal to 0. For a conservative system, the applied force are derivable from the potential energy V. So sigma I varying from 1 to n Fi are delta ri delta v is equal to delta v. Hence the equation 2 becomes integral t1 to t2 bracket start delta t minus delta v bracket close dt is equal to 0, but delta bracket start t minus v bracket close dt is equal to delta bracket starts t minus v bracket close dt plus bracket starts t minus v bracket close delta bracket starts dt bracket close, which is equal to delta bracket starts t minus v bracket close dt, because delta bracket starts dt bracket close is equal to d bracket starts delta t bracket close is equal to 0 square bracket close. So integral t1 to t2 delta bracket starts t minus v bracket close dt is equal to 0, or delta integral t1 to t2 bracket starts t minus v dt is equal to 0, or delta t1 to t2 L dt is 0. Hence integral t1 to t2 L dt is a stationary.